Hello everyone, welcome back. So in this video, we will solve some interesting problems on a dynamic programming. So let's just start with one of my favorite problem, another count bits problem. So in this problem, for a given integer n, you have to print the number of set bits in each integer from 1 to n. So for n is equal to 5, this is the expected output. So let me explain you the sample input and output first. So for a given integer n, you have to print the number of set bits in all the integers from 1 to n. So for n is equal to 5, integer 1, the binary representation of 1 is 0, 0, 1. I am writing in terms of 3 bits. Then for 2, 0, 1, 0. Then for 3, 0, 1, 1. For 4, it is 1, 0, 0. And for 5, it is 1, 0, and 1. Cool. So how many set bits are there? 1. Then the number of set bits, again 1. Then the number of set bits 2. Then the number of set bits 1. Then the number of set bits is 2. So this is the expected set of outputs. So what is the naive solution? So the naive or the brute force approach is very straightforward. That is, iterate over all the integers from 1 to n and then count the number of set bits in integer I. So write a function count bits for integer I, and this function will return you the number of set bits in integer I. And I'm assuming that you guys are already familiar with bit manipulation basics, and you can simply write this function in log of I base 2 times. So then I will simply return this integer, that is number of set bits in integer I. So what is the time complexity? So the time complexity is n, as we are iterating over all the integers from 1 to n, that is n iterations, and then log of I base 2 times. And the value of this I is up to n, so it is log of n base 2. So this is the time complexity. And can we do something better? And yes, definitely we can do something better. And the idea here is to use a dynamic programming. So let me just quickly define a state, which is the first step for my state. So let's say dp of I as the number of bits in integer I. So to solve this problem using a dynamic programming, you just need to know about two operators, that is left shift operator and a right shift operator. So what is the value of a left shift b? Isn't it a multiplied by 2 power b? And what is the value of a right shift b? So it is a divided by 2 power b. Cool. So let me just quickly write in this way. So let's say 13. So the binary representation of 13 is 1 1 0 1, 8 plus 4 and plus 1. So then what is the value of 13? Left shift 1. That is, we shift all the bits one position in the left hand side, and 1 0 will be added in the place of LSB. So 1 0 1 1 1 0 1 and a 0 will be added. So this is nothing but 26, that is 13 multiplied by 2 power 1, which is equal to 26. And how I can write a 27? So that is 13 left shift 1 and plus 1, that is 1 1 0 1, and instead of 0 now we are having 27, that is 1. So how many number of set bits are there? So the number of set bits here are 3, and there is no change because we have just performed a left shift operation, and that is added a 0 on the left hand side, sorry, on the right hand side in the place of MSB. So we have added an extra 0, that is, there is no change in the number of set bits. So this is remain 3, and here the 0 has been changed to 1, so it is 4. That is 3 plus 1, which is equal to 4. So can I write in this way? That is, can I write this recurrent solution? Dp of I, it is equal to dp of I by 2 and plus 1. That is, the number of set bits in I is equal to the number of set bits in I by 2. If I is completely divisible by 2, otherwise we add 1 if I is odd. So if I mod 2 is equal to 1. So if it is odd, then I will add 1, and if it is even, then the number of set bits in I is exactly equal to the number of set bits in I by 2. That is, the number of set bits in 26 is exactly equal to the number of set bits in 13, because we have just performed the left shift operation, that is added a 0 on the right hand side. Cool. So this is the recurrent solution, and the base case, if I is equal to 0, that is, the number of set bits in 0, dp of 0 is equal to 0. So yeah, this is the state, recurrent solution, and base case. Let me just quickly code this up. So take an integer n from the user, then my dp array. So int dp of size n plus 1. dp of I is number of set bits in integer I. And here I'm writing a bottom up solution. You can write a top down, that is recursion plus memorization by yourself. So dp of 0 is equal to 0. Then I iterate over all the integers from 1 to n, and dp of I is equal to dp of I by 2, and plus 1 if I is odd. So that is I and 1. So if I is odd, then I and 1 is equal to 1. So we are adding 1 in my answer. And if I is even, then I and 1 is equal to 0. That is, we are adding 0 in my answer. So this is something that we want. You can also write a if condition. If odd, add 1, otherwise nothing, add 0. But this is the smarter way of implementation, and I will print the value of dp of I, that is number of set bits in integer I. So let me test for n is equal to 5. So for n is equal to 5, this was the expected output. Cool. And the time complexity is linear O of n, and the extra space that we are using is also linear because of this dp array. So this was all about this problem. Let's just solve the next problem, which is minimum steps required to reach n. So you are given a positive integer n, and you have to reduce it to 1 by performing the following steps. So the first step, in the first step or operation, you can reduce n to n minus 1. The second operation, where you can reduce n to n by 2 if n is divisible by 2. The third type of operation, where you can reduce n to n by 3 if n is divisible by 3. So definitely we have to minimize the number of operations that we perform to reduce n to n by n to 1. So for n is equal to 16, the expected output is 4. That is, reduce this 16 to 8, then 8 to 4, 4 to 2, and 2 to 1. So pause the video and try to think of a solution. And first try to find a greedy solution. And if your greedy solution is not working, then explore all the possible paths and write a formal state, and then write a recurrent solution. If there is an overlapping subproblem, then memorize it using dynamic programming. So our goal is to reduce n to 1. So it's not always about to directly start with a dynamic programming solution. Just write a greedy solution, propose some greedy solution, and check your greedy solution is correct or not. And the best way to correct yourself, the best way to prove yourself correct is to prove that you are not wrong. So for your greedy approach, propose some for your proposed greedy approach, write some test cases and check your test cases will pass, your greedy approach will pass that test cases or not. And if you find some test cases for which your greedy approach is not working, then update your greedy approach. And if you still find some test cases where your greedy approaches fail, then write a recursive solution, that is, explore all the possible configurations and find the best solution. So for we have to reduce n to 1. So for 16, what I can do, I can use the operation of second type, n to n by 2, because it is divisible by 2. Then again n to n by 2, then again n to n by 2, and again n to n by 2. So how many operations we required? So 1, 2, 3, and 4. So in this case, my answer will be 4. So what is the best greedy solution that might come to your mind? The best greedy solution is that we have to reduce n to 1. So we try to reduce n as much as possible. That is, we give n to n by 3 as the first. This is my first priority, then the second priority, and otherwise we reduce n to n minus 1. Cool. So the best greedy approach is to reduce n to n by 3 if it is divisible by 3, and if it is not divisible by 3, then check for n by 2. So that is, if n mod 3 not equal to 0. Cool. Then I try to divide it by 2, and if it is still not divisible by 2, that is n mod 2 not equal to 0, then I had no other option, so I will reduce n to n minus 1. But this best greedy solution would not work for all the cases. So let me just give you an edge case for n is equal to 10. This greedy approach would not work for n is equal to 10. So for 10, what you can do, you will first check for n by 3. So not divisible, then you will check for n by 2. Divisible, so we'll divide it by 2, 5. Then we check for Then this is the new value of n. So again I will check for n by 3, not divisible, n by 2, not divisible, then n minus 1. Cool, 4. Then for this 4, not divisible by 3, divisible by 2. So we'll reduce it to 2. Then for this 2, not divisible by 3, but divisible by 2. So reduce it by half. So it is 1. So this is the greedy path. And if you follow this greedy path, then you claim that your answer is equal to 4. That is the minimum operation that we required. 1 operation, 2 operation, 3 operation, and 4th operation. Cool. But you can memorize this operation, that is number of operations is equal to 4 further. That is, you can reduce 10 to 1 by just using 3 operations. And let me tell you how. So first reduce this 10 to 9, and then this 9 to 3, and this 3 to 1. So you can see in this case you just only require 3 operations. So this was the greedy path, and this was the best path. So the greedy solution, the greedy approach would not pass for all the test cases, and here is the corner case. So now we do not have any other option except to explore all the possible paths. Now let me just quickly form a state. So let's say f of n as the minimum number of steps required to reduce n to 1. Then what will be the recurrence relation? So f of n is equal to f of n by 3 plus 1, and definitely we call this function if and only if n divisible by 3. So that is n mod 3 is equal to 0. The other option that I had, that is I will explore every path. Let's say it is 12. So I will divide it by 2, that is 6. Will divide it by 3, which is 4. And I will also reduce it to n minus 1, because there might be a case when n minus 1 path is the best one. So yeah, I will try all the possibilities. So then n by 2, and since I have performed one operation, so we'll add 1 here. And definitely if n is divisible by 2, then only I will call this function n mod 2 is equal to 0. Otherwise f of n minus 1. Cool, and plus 1. And since my goal is to minimize the answer, so I will take minimum out of all the 3 possibilities. And what would be my base case? That is f of 1. So the number of steps required to reduce 1 to 1, isn't it 0? The minimum number of steps required to reduce 1 to 1, 0, right? And now you know the state, definition of state, recurrence relation, and base case. So let's just simply code this up. And again, I'm going to write a bottom up DP. You can implement the top down DP, that is recursion plus memorization by yourself. So simply taking this integer n as an input, and then my DP of size n plus 1, then DP of 1 is equal to 0 for I is equal to 2 till n. So first I will initialize DP of I with some maximum value, and then I will check whether it is divisible by 3 or not. So if it is divisible by 3, then DP of I is equal to minimum of DP of I, comma, DP of I by 3 and plus 1, since we have performed one operation. Then don't write else case, because we have to explore all the path. So not else, but if only. So if I mod 2 is equal to 0, then DP of I is equal to minimum of DP of I that we encounter so far, and DP of I by 2 and plus 1. Cool. And for I minus 1, we don't have to check anything. And finally, I will print DP of n, which is my answer, the minimum number of steps required to reduce n to 1. So let me just quickly test for 16. The expected output was 4. Yeah, 4 it is. Then for 10, the expected output is 3. So we got 3. And what is the time and space complexity? So the time complexity in this case is linear, since we are iterating from all the integers from 1 to n. So linear time. An extra space that we are using is this TP array, which is again linear. Cool. So this was all about this problem. Let's just move on to the last problem of this video, which is a partition problem, rod cutting. So again, I would highly recommend you guys to pause the video, read the problem, and try to think of a solution. So given a rod of length n and array prices of length n, denoting the cost of pieces of rod of length 1 to n, and we need to find the maximum amount that can be made if the rod is cut optimally. So for n is equal to 4, this is the expected output. So this is the final problem of this video, rod cutting, which is very similar to the previous problem. So I highly recommend you guys to pause the video and read the problem statement, try to think of a solution. So given a rod of length n and array prices of length n, denoting the cost of pieces of rod of length 1 to n. So we need to find the maximum amount that can be made if the rod is cut up optimally. So for n is equal to 4 and this prices array of length 4, the expected output is 20. Here one base indexing has been considered, that is prices of 1. Here 1 is the index, is representing the cost of length of rod 1, prices of 2 is representing the cost of rod of length 2, and so on. So let me just quickly explain you the sample input and output first. So we have a rod of length 4. So how we can cut this rod? The one way is to cut this rod into 4 chunks of length 1 each. So 1, 1, 1 and 1. So then what would be the cost, inner cut cost? So 1, 1, 1, 1. So the cost of rod of length 1 is 3. So that is 4 into 3, which is equal to 12. Cool. What is the other way to cut this rod? We can cut this rod into two chunks of length 2 and 2 each. So 2 and 2. Then the inner cut cost is 2 into 5, because the cost of rod of length 2 is 5. So 2 into 5, which is equal to 10. Cool. The other way is to cut a rod of length 3, rod of length 4 into 2 chunks, one of 1 and 3. So in this case, the inner cut cost of 1, 3 is 3 plus 4, which is equal to 7. And if you cut the rod into 3 and 1, then the inner cut cost would be same. So 1 and 3 and 3 and 1 both will give you the same answer. Then finally we do not cut this rod. So in this case, the inner cut cost is 20, because the rod of length 4 is having price 20. And since our goal is to maximize the amount, so the maximum here is 20. That's why the expected output is also 20. So hope the problem statement is clear to everyone. So this is the dynamic programming solution. Any greedy solution would not work here. You can try it by yourself. So let me just quickly form a state. So let's say TP of n as the maximum amount that can be made. The maximum amount that can be made by rod of length n. So what is dynamic programming? It's basically memorization of states. So we explore all the possibilities for every state. And if there is an overlapping subproblem, then just simply memorize it by either using top-down DP or a bottom-up DP. It's totally up to you. And this time I will code the top-down DP, and the bottom-up DP is for you. That is iteration. Top-down is recursion plus memorization. So if this is the definition of my state, then what will be the recurrent solution? So let's say you are given a rod of length 8. So let's say the rod of length 8, and let me also write a prices array of length 8. So the price of rod of length 1, let's say it is 2. Then for price of rod of length 2, let's say it is 4. Then 5, 7, then maybe 3, and let's say 6 and 10. Cool. And this is 7 integers. Then the rod of length 8, let's say it is having price 12 maybe. So what will be the recurrence relation? So for DP of 8, what I can do, I can cut this rod. Basically, I have to explore all the possibilities. So from this rod of length 8, I can cut it into two parts. That is, I can extract a rod of length 1 from here, and then this is the remaining subproblem. That is, what is the maximum amount that I can make from rod of length 7. So can I say this thing? DP of 8, it is equal to price of 1. Let me write P. So here I'm writing P in place of this price. So P of 1. And here I'm considering 1 base indexing. You can consider 0 base indexing. But yeah, it's totally up to you. So P of 1 and plus DP of 7. I have extracted a rod of length 1 from here. Then this is the remaining subproblem. Cool. Then the other option that I have, extract a rod of length 2, and then the remaining subproblem, which is the maximum amount that I can make from rod of length 6. So remaining subproblem, so price of 2 and plus dp of 6, the maximum amount that I can make from rod of length 6. Cool. And so on for 3, 4, 5, 6 and 7. Then what I can do, I cannot cut this entire rod, that is this rod would remain as it is. So in this case, price of 8 plus dp of 0, right? So this would be my base case. And since our goal is to maximize the answer, so I will take maximum out of all the possibilities. Cool. And this is my base case if the value of n is equal to 0. What if the value of n is equal to 0? So in this case, what is the maximum amount that I can make? So the maximum amount that I can make is also 0, because no rod, no price. Cool. So now you know the state, you know the recurrence relation, and you know the base case. So try to implement the solution, and let me just quickly again summarize it. So dp of n, it is equal to summation of from 1 to n, and maximum of dp of I, not dp of I, but actually the price of I plus dp of n minus I. Cool. And yeah, this is the base case. So let me just quickly code this up. And how I come up with this recurrent solution. So dp of n, the maximum amount that I can make here, basically this is just a summary. So the maximum amount that I can make from rod of length n. So then here I will iterate over all the possible values of I, that is possible values of rod, which I can extract from the rod of length n. So it is from 1 to n. Then if I cut a rod of length I from n, then this is the remaining length. So dp of n minus I, and I will get the price corresponding to it. So yeah, so let me just start from the very scratch. So simply I'm taking an integer n. Then here I will make this a price array as a global array, and even it's not recommended to make things global, but since this is an educational video, so that's why I'm writing this array globally. So assuming the standard limit, so constant int n as 10 power 5, because generally the size of the array that will be given to you in most of the problem is around 10 power 5. So 1 followed by 5 zeros, and plus some constant, just to be on the safer side, to do not go out of bound. So 10 power 5 plus 5. So yeah, and for the current n, let me just quickly take zero base indexing or one base indexing. And one more thing, the global arrays are initialized with 0, not with the garbage values. So dp of 0 is equal to, or dp not dp, but price of 0 is equal to 0. Cool. So I will start taking the input from 1. So I is equal to 1, while I is less than or equal to n, I plus plus c in price of I, that is price of rod of length I. Cool. And then I will simply print rod cutting. So this is a recursive function, and here I will pass the current value of n, that is the current length of rod. So it is initially n. I wanted to know the maximum amount that I can make from n. So int rod cutting and int n. So if n is equal to 0, then simply return 0. No rod, no price. Otherwise, what I can do, I can iterate over all the possible lengths and extract I from here, and I will initialize my answer with 0. So answer 0, and then answer is equal to max of answer, comma, price of I, and plus rod cutting of n minus I. So this is the recurrent solution, and finally I will return this answer. So let me just quickly test it. For the given input 3, 5, 4, 20. So n is equal to 4, and 3, 5, 4, 20. Here the expected output was 20. So here it is same as the expected output, and this is a recursive code. Now let's just analyze that whether there is an overlapping subproblem or not. So yes, there is an overlapping subproblem, because if you draw this recursive tree, then from here what you can do, from rod of length 7 you can extract a rod of length 1, and then solve the remaining subproblem. So this dp of 7, so here what I can do, I can extract a rod of length 1 from this rod of length 7. So that is price of 1, and then solve the remaining subproblem plus TP of 6. Cool. So if you have noticed, this subtree and this subtree gonna be exactly same. So isn't it there is an overlapping subproblem? So there is an overlapping subproblem. So definitely I'm going to memorize the answers. So int memo and of size n, then memset will set every value, every index value to -1. So 3 parameters are required for this memset function: base address -1 and size. So size of memo. So first I will check whether I have already computed this answer or not. So if memo of n not equal to -1, that is, it is not equal to the default value. So we have already computed the answer for this state. So simply return it. So return memo of n. Otherwise, compute the answer, store it, and then return it. So let me just build this program for one more time. And yeah, we got the same output. So what is the time complexity? So the time complexity for recursive functions, let me just give you a general idea to find the time complexity for recursion. So time complexity of recursion. So it is equal to number of different states, or you can say different function call, multiplied by time complexity of each function. So for this case, the time complexity, the overall time complexity, how many different functions we are having. So we have memorized the answer. So how many different values of n? So isn't it n? The initial value of n. So it is n into n. And why this n? Because this is the number of different functions, but the time complexity of each recursive function is also n, because we are having this loop from 1 to n. So it is n square. This is the time complexity. And what is the extra space complexity? So as an extra space, we are using this memo array. So it is also of length n. Cool. So this is all about this video. We have solved 3 problems on dynamic programming. So yeah, thank you so much guys for watching this video.